Good morning, everybody. Welcome to our science seminar for this Thursday. And you'll be happy that it's not me giving the seminar. This week we have with us Dr. Xiao Li from University of North Texas. We've had a lot of students from chemistry go to University of North Texas into their chemistry program there for a PhD. And now we have material science engineering coming from UNT to get more of you guys to come and join their program over there in graduate studies in material science engineering. Dr. Li got her bachelor's degree in China at Wuhan University of Technology. She also got her PhD in China from the Chinese Academy of Sciences. Then she came to the U.S. and worked at the Argonne Research Lab over there in Chicago, part of University of Wisconsin, was it? And she's been about almost 9 years there. About there. And then from there, she came to University of North Texas, which is just north of Dallas there in the Denton area. Okay? And today, she is here to tell you all about material science engineering and what careers that you have available to you, and opportunities to do graduate studies in material science engineer. And I hope you'll give her a warm welcome.
Good morning, everyone. Thank you very much for the kind invitation. It's my pleasure to be here today to introduce a little bit about the research work, exciting research work going on in my lab. So today my topic will be the self-assembly of soft materials. I don't know how many of you familiar with material, especially soft materials. If I mention the soft material, can you name one or two that you think that is belong to this category? So yeah, it's fine. If you look around, look at this plastic table or the chair or fabric over there, or look at the computer. Those are from the soft material we refer polymeric material, right? That is one good example. Another one is look at the screen. That if you know that the liquid crystal moleculars are the major technique that to made for these displays, that is also referred as another soft material. So I'm gonna give some detailed information later on. But today, my topic will be focused on one of the soft materials called blue phase liquid crystal, which can form in three-dimensional structure. And those three-dimensional structure can be tuned to be used as photonic crystals, sensors, displays, and wearable devices. So it will be very interesting. So first, before I start my research part, here are a few slides I were given by my department chair that I was requested to present here to introduce a bit about our university, University of North Texas. So UNT is a Tier 1 research university and also a Hispanic minority serving institution. We have a large student population. And for the College of Engineering, which is located separate from the main campus. The main campus located southeast of Denton, but the College of Engineering that we call the Discovery Park, that is located a bit north of Denton. So in the Discovery Park, this College of Engineering, we have the Department of Material Science, Biological, EE, Mechanical, and Computer Science. So all the labs, classrooms, office are located there, and the people over there, faculties, research group collaborate a lot. Okay, so here are the 5 departments in our College of Engineering. And here are a few numbers to introduce more about the research funding and ongoing research and the student diversity. And also you can see here in our College of Engineering, we conduct all kind of different researches regarding the health science, the advanced manufacturing, and also the sensor systems, additive manufacturing, artificial intelligence, and machine learning. And we also have large research facility centers, which we have the additive manufacturing center. We also have the advanced material processing institution, also the cybersecurity and the center for the information, and the center for the integrated intelligence mobility systems. So those large research centers provide a very good platform for students to conduct the research, and we have a lot of good shared facilities that is available for students for your research over there. Okay, I finish this part here. So we going to the today's topic about the soft material. I already named two examples, polymer and liquid crystal. Actually, for the soft material, it also includes the surfactant. So detergent, which you can think of the most like recognized surfactant, which ramp up the oil and can be dissolved by water. That's why you can clean up your dishes, you can clean up your clothes. That is the surfactant. Surfactant of basically the amphiphilic molecules. One of the part of the molecular can be dissolved or interact with water, the other and can be interact with oil. That's why the oil can be taken away by the detergent, washed away by water. So polymer, I already have the examples. So actually polymer has construct a lot of good product in our daily life. The table, the computer, laptop, the chairs, some of the furnitures, and the window glasses, all kinds of things, you can name it. And membranes that is like the usually existed in the, for example, the lipid membrane that to facilitate the breath of your skin, and also glasses and the liquid crystal that were the most familiar case. That is the case that liquid crystal made the display back over over like a decades ago. That is now very popular mature technologies, and also colloidal particles and the biological systems. So if you look at the length scale here for the soft material, they often locate a few nanometer to like up to a few micrometer or below 1 micrometer. They are with very like small size regime. So whenever you consider the soft material, that is actually you consider the interaction between molecular is relatively weak. When I mention it is weak, you can confer or you can refer or compare to the metal material or the ceramic material, which in the metal material you will expect a much strong interaction between the atoms, and which we refer as the primary bond. So there are 3 types of primary bond: metallic bond, ionic bond, and covalent bond. In addition to those 3 primary bond, we also have the secondary bond. So the secondary bond, the bonding energy will be much weaker than the primary bond, which is also the major mechanic that can be happened for the self-assembly of soft material. So here gives you an example. It's about the van der Waals force. If you think 2 particles, they separate far from each other, and then you bring them together. When the distance decrease, you will find they first they're gonna experience the attractive force, and such kind of attractive force reach to the maximum point. And then if you push them further together, the repulsion force will dominate. They try to separate the particle. So here will be an equilibrium state that the 2 particles stay very well, interact well, stay happy with each other, and there will be interaction forming between each other. So that is the interaction we refer as the secondary bond, which is relatively weak. But the advantage for such kind of weak bond, which means any small perturbation that you provided, all the thermal fluctuation that you provided in the system can easily break or rebound those two particles. So that is the magic of the soft material, that they can they can assemble into a certain pattern. And meanwhile, you can use either thermal or external field, a relatively lower amount of energy to easily break those bonds, to reconfigure them into another pattern, which is not available for those metal material. For metal material, usually you have to heat up the material up to their melting temperature, which often is 1,000 degree. Degree. So that is pretty much a large amount of energy you have to provide it into the system in order to break the bond. However, here for the softer material, just a small, sometimes the energy you provided will be just a few kT, that is, which means the system can be reorganized even during the room temperature. So in order to better understand what I'm talking about, the self-assembly, here is some indication from the nature that the size apparently is orders of magnitude larger than the moleculars I referred. But here can give us an idea how when I mean the self-assembly, what does that stand for? So here are two pictures, which is a school of fish and a group of birds. If you have looked into those two species, that often they have large group of birds. They don't contact or they don't hold hand to each other. But when there are large group of birds, they can do such kind of collective motion. They kind of fly towards certain direction, or they fly forming certain pattern. So which they still, that is the same for the biologists, that they to study why this active matter, we refer this as active matter, can take such kind of collective motion. It is still some of the ongoing research. But here I want to mention that if you scale down the size of individual those birds or fish into a nanometer or angstrom scale, that you can think of individual those fish or birds as a molecular. So for the molecular, they also have such kind of ability, but we know that is because of the interaction between moleculars. For example, the van der Waals force, when they are too close to each other, they start to create this weak bond to bond each other. Therefore, they can do the motion together, which we refer as the collective motion. So in the nature, people already found a lot of interesting, if we take one example, liquid crystal. So in the nature for the fruit, plant fruit, or our DNA, or some of the beetles' shells, we already observed those wonderful colors which represent the orientation or the organization of those molecular into a particular regime or a direction. That's why when they interact with the incident light, they will reflect certain wavelengths of light. Therefore, you will see such kind of vivid color. So as I mentioned, the liquid crystal, when it is first developed, that is major use to construct the display. But for recent years, it has been used a lot to create those new technologies. For example, to use the liquid crystal to fabricate the wearable device to detect the health or monitor the health system of the human body. And also it has been used as sensor, since it has the vivid color. Through the color change, it can indicate, whether there is small dose of certain toxic chemicals or other materials in the system. And also it can be created as into the metastable state or metastructure to construct the optical devices. So speak to liquid crystal, that is state of matter that stay between the solid crystal which we can refer as the metal material. All the atoms has been pinned down in very particular position and interact with each other. So that is the solid state crystal. And between isotropic liquid, which is the water, that you can think of the water molecules, they can flow without any restriction of the orientation or the direction. So liquid crystal is kind of the material that located just between those two. It has the ability to flow as a water, but meanwhile it keep ability that under certain condition it can form like ordered three-dimensional structures. So that is the liquid crystal. So if you look at the liquid crystal, the typical molecular chemical structure that it often contains two benzyl rings, and then you will have a terminal chain which often carbon chains, a few carbon atoms connect as the tail, which provide the flexibility, which provide the ability of the molecule to kind of move around. So the other end often ended up with the electric dipole molecular or group, which can be polarized by the external field, which that is also the reason that liquid crystal molecules often can respond to the electric field, magnetic field. So if you take this like chemical structure as the overall like the shape of the molecule, you can think of it as a short rod. So you can picture it as a short rod with the length about 1/2 nanometer. Oh. Oh, here we go. So you can picture it as 1/2 nanometer length and a half nanometer width. So we consider this as a birefringence. It has the birefringence property, which means when an incident light goes, it will split the light into an ordinary and extraordinary waves. So when those waves comes out of the liquid crystal material, because of the interference between those two pathways, they're gonna generate different color based on how retardance distance of those two wavelengths or two paths. It will reflect different colors here. So which means okay. So which means that we can, when we place the liquid crystal into orthogonal polarizers, then you're gonna have the polarized light in. When you play with the position of those liquid crystal material, it can alter or change or adjust the direction of the polarized light. When it goes to the analyzer, it chooses to either block the light or transmit the light. That is actually the working mechanism for all the displays, that if you consider each pixel, you have those materials, and you have the light goes in, those for each pixel that you can control the orientation of the liquid crystal, selectively transmit or block the light, then you will have the pattern or the image showing on your display. So for the liquid crystal, the two major features that we already talked about is one, because of those asymmetric molecular shape, they have the ability to align along certain direction. And such kind of long-range order can go through above like micrometer scale. Even though the size of the molecule is really small, just 1/2 nanometer. However, the order can translate from one end to the end. The distance over here will be a few tens micrometer scale. So there will be like here compared to I showed two images. That is, I took the image that if you imagine the wood flowing on the river, that individual wood you think of as individual molecules, that they often prefer to align or squeeze together. That is also happened in the liquid crystal system, that you see here all those different color zones. That is different oriented liquid crystal molecular here. So when you have the different regions of or domains of liquid crystal molecular that they oriented in different way, which looks like all those canoes that if you see that they have following certain pattern in certain area, and when two area that is following different direction, there will be a defects generated. The similar as the liquid crystal system, for all those like uniform color area, you can imagine all the liquid crystal molecular, they are oriented the same way. So whenever they interact with another domain which oriented in different way, there will be a defects generated here. So in terms of how those defects forming, we name it as +1, -1, +half, -half defects generate here. So those two major features for liquid crystal give us ability to first tune the alignment or the orientation of the liquid crystal, which you can control what kind of color can be reflected. And secondly, those topological defects, I will talk a little bit later on, which is also very important because whenever there will be a topological defects created, which means those regions, all those molecular are in a chaos state. They are very disordered. So disorder, which means they're gonna raise higher energy over the local area. So whenever, imagine if you have another particle comes into the system, so the particle would probably go into this high energy area to occupy this high energy area in order to minimize the whole overall energy of the whole system. So that is also later on, like I will show the work we use to use those topological defects to purposely trap the nanoparticles into the system. So again, for the liquid crystal phases, as I already introduced, that is the most common or simple liquid crystal phase we refer as nematic phase. In the nematic phase, we only consider one orientational order. Actually, in the liquid crystal, there are two different categories. Today, we're going to focus on the thermotropic, which means the temperature will be the dominant parameter to change the phase of liquid crystal. There will be another category which we refer as lyotropic, which the concentration of the material is the way that to create different phase or trigger the phase transition. So here, in addition to the nematic phase that I just mentioned about that we only care about this orientational order, there will be also thematic phase. In addition to the orientational order, we also have their layer structure forming, which we refer as the positional order. So the thematic phase, we combine the orientational and the positional order. And there will be also chiral phases. When we're talking about the chiral phases, which means that we adding the chiral dopant into the nematic phase. So in the nematic phase, if you picture each molecular as a like rod, they orient in this way. So when you add the chiral dopant, the molecular start has the ability to twist. So it will start with one position, slowly twist, end up with another position, opposite, and until they resume the original position. That will be a one period of those twists. So that will be the clasteric phase. So for the clasteric phase, if you look at the schematic showing here, because of the rotate of the molecular, actually you can control the lead to interference with those clasteric liquid crystal. And by changing or varying the pitch here, you kind of can control which wavelengths of the incident light will be eventually reflected out. So that's why that for the clasteric phase, usually you will also observe very tunable or controllable different colors. So here, to the topic of our today's today's talk is the blue phase. So blue phase actually is when you add the chiral dopant and you add quite amount of the chiral dopant. So the molecular start to twist not only along one axis, it along all kinds of axes around this cylinder, so which we refer as the double twist cylinder. And the double twist cylinder can further reorganize themselves into a three-dimensional structure. So in this video, showing better, yeah. Okay, so chirodopin and adenine molecular start to twist, and they twist all kinds of directions, forming this double twist cylinder. And the double twist cylinder start to reorganize them into a three-dimensional structure. For all those areas that double twist cylinder cannot fill in, that will form the topological defects. So here, instead of point defects, it will have this line defects. So this is that eventually those form the structure containing the topological defects, and the double twist cylinder we refer as the blue phase liquid crystal. So it is very useful because when we consider about the lattice parameter A, which is the each unit size, and also which kind of lattice crystalline structure forming, we can use the material when you have the white light in, and by changing or tuning the structure of the blue phase, you can selectively reflect just one particular wavelength light. So overall, you will see the film as either blue, red, or other colors. That is quite useful, and meanwhile, the blue phase has the very rapidly response time compared to other nematic liquid crystals. So that's the emerging new material to construct the new display. And meanwhile, it can be used as a photonic crystal to tune the different wavelengths, as well as the sensors. For example, here, if you observe the color change from red to green, which indicate certain of the here they have some of the biomaterial added into the system, so you can detect whether there will be additional composite into the system. So, however, in order to use such kind of blue phase liquid crystal material, they have some of the limitations. First, because the blue phase that we I forgot to mention, they have two different phases. Blue phase 1, which often forming the body-centric cubic structure. Blue phase 2, which often forming the simple cubic structure. So blue phase 1, which for both of the cubic structure, they're gonna have the different lattice orientation. For each lattice orientation, they're gonna respond to particular wavelength light to be reflected. Therefore, that when you look at the material, they are not uniform color. They always lack multiple colors showing here. That is because they have multiple oriented domain inside of the system. However, either you use it for the display or use it for the sensor or the photonic crystal, you always want to control, there will be just a controllable one particular color can be generated. So here, showing that a different way that people used to modify the surface in order to control the lattice orientation, eventually will be just one monochromatic light generated here. So for example, people use electric field or surface rubbing or the thermal gradient to kind of slowly growing those kind of crystal material to have a uniform monodomain surface. So from our perspective, we also consider that how we can control the growing of a large area single crystal of those material. So one possible way that we think about is if we start with the most simple nematic liquid crystal, as I mentioned, you can treat it as a short rod. And by surface chemical modification, we can easily control to align those liquid crystal either perpendicular to the surface or parallel to the surface. So if we have such kind of ability, and by tuning, here is the polymer brush that we synthesized, which contains a such messaging can interact with the nematic liquid crystal. Therefore, by changing the grafting density, we can easily tune the anchoring or the alignment of the liquid crystal from perpendicular to parallel. So by this way, we further test that if we have such kind of layer modify the substrate, and then we start to open trench on the substrate, and we found that by varying the width of the trench opened on the substrate, we can easily control the liquid crystal all align along this trench direction at certain width range. Otherwise, if you fell below this range, it will be uniform homeotropic, uniform like stand-up alignment. Or if above this range, it will be like degenerate planar, which means there will be lost control of this preferential orientation. So by this, with this information, we further design the pattern that with a 45-degree intersect but not touched pattern over here. So for those areas that two lines comes to each other at the joint point, there will be a generated a little distorted area we refer as the point topological defects. So later on, when we introduce the colloidal particle or nanoparticle into the system, you will see that the particle naturally goes into those high energy points and occupy those topological defects locations. And those methods can bring a pair of, can create a array of pair of those colloidal particle and can bring those two particles very close to each other. That is based on the middle line you create here. The minimum size we get is like about 15 nanometer, which you bring those two nanoparticle. The nanoparticle used here is around 800 to 1 micrometer scale, and they can be very close, around 15 nanometer to each other. So with all those information, back to the more complicated three-dimensional blue phase material. Here, when we look at one unit cell of the blue phase, all those like colorful short lines represent the small molecules, how they oriented inside of the system. And the gray bars here represent the topological defects, which means, as you remember in the cartoon showed, when the double twist cylinder cannot fill into the space, all those space, they are not empty. They actually filled with all those disordered molecules. So that is one unit cell of those material. So then we start to think about, we start to control the surface anchoring by combining those material, which is liquid forming, into a two substrate, and then we play with the surface modification of the substrate, and we can see that the system, by increasing the temperature, they go different phase, cholesteric phase, blue phase 1, blue phase 2, eventually goes to the isotropic phase. However, here with the homogeneous surface, we cannot control any of those lattice orientation. You still end up with a multiple domain configuration. So here, take a step further that we use the combination of the planar and homotropic to create a chemically patterned surface. The pattern was very simple, just a straight line. And on the straight line, you will expect the alternating anchoring, which means the liquid crystal molecular will be perpendicular, parallel, perpendicular, parallel. Just with such kind of simple pattern configuration. By increasing the temperature, and we found in the blue phase 2 regime, right on the pattern area, we end up with a beautiful single crystal reflect all those blue color, which represent the blue phase 2 100 orientation. By keep increasing the temperature, it will goes to the isotropic. So here shows you that seems like the stripe pattern has the magic to stabilize the blue phase 2 100 lattice orientation. You end up with a quite large, beautiful single crystal. So if we look into the science behind, especially we look into the interaction between the material and interface, that we conduct the computational simulation here, that we found out when the liquid crystal materials start to interact with the substrate, the molecular at this interface, they prefer to take this alternating alignment planar homeotropic, planar homeotropic. And so we interpret such kind of formation of the liquid crystal into a pattern that is which has the alternating homeotropic and planar. And by calculating the overall free energy of the system, we found that when those planar homeotropic strap widths equal to each other, that will be the lowest energy point. That is also the process or the reason how we end up with this pattern design to stabilize that specific Blueface 2 100 plan. And following the same logic that we create the different pattern that in order to stabilize the Blueface 2 for the different lattice orientation, for example, 110 or 111. When we apply those patterns on the substrate and we conduct the experiments again, and if you look at the Blueface 2 temperature regime, and on the pattern area, they all forming such kind of quite uniform single crystal domain. And later on, we have the cursor diagram, which is the technique that we use the optical way to interpret the lattice orientation. That we found, okay, all the blue color that showing here, which has the circle represent the 100. And we also observe the two curved line, which is the 110, and also have the 3 of 6 curved line represent the 111 lattice plane. That is all showing here. That is the cursor diagram to indicate, even though those are black area, actually they are different lattice orientation. That is for the Blueface 2, which has a simple cubic structure. So for the same mechanism we apply to the Blueface 1 by carefully design the pattern to apply to the material, that we have this diamond-shaped cursor diagram to indicate the Blueface 1 110 lattice orientation was stabilized under the pattern, right on the pattern area. So here we show the ability that by just simply tune or pattern the surface, you can easily control which phase you want to stabilize, and in each phase which lattice orientation you want to stabilize. And it depends on how large area patterns surface you can generate. It will form this beautiful single crystal on top of it. So here we considering about the green boundary. Green boundary, as I mentioned, here gives you the example of the polycrystalline metal material that whenever two different domains they come to each other with different orientation, there will be a green boundary generated. The same as the polymer material, when different oriented like polymer domain comes to each other, you will have this like polygreen boundary greens. So here we kind of use such kind of, as I mentioned, we have the ability that by tuning by patterning the chemical pattern on the surface, we can selectively stabilize Blueface 2. And here showing you that based on just the strap pattern, if we carefully control the dimension, you can carefully control like within a very narrow range that you can play with to all generate those beautiful single crystal. So here we kind of considering the green boundary as well as the interface, especially green boundary that is from the solid crystal material. But if you consider the liquid interface, the liquid interface also very important. For example, it can support the soft membrane self-assemble at the interface, and it can like locate the colloidal particle at the interface. It can also censor the biological toxins and to transit the ions at the interface. So the liquid interface is also very useful. But as we all know that it is easy to control not easy actually, but it will be a way to control the green boundary in the metal material solid state. However, it will be very hard to control the green boundary in the liquid phase, right? Because they are isotropic fluidic. Here, based on our system, the liquid crystal, which combines the solid and the liquid phase, and we have the ability to stabilize a certain phase, whether we have the ability to maintain the green boundary if we do the design. Here is the design flow that we considering that we have the two different patterns adjacent to each other to examine whether the crystal boundary can be remained over there. So here we conduct first of all, if without any green boundary, without any design adjacent pattern, the crystallization forming on the pattern area probably going to propagate, which we refer as the propagate length will be the coherence length that the orientation can be transferred outside of the pattern area. So here we examine that we start to pattern those two different geometry pattern adjacent to each other, and we found that actually when you have the strap and the rectangular pattern adjacent to each other, you're going to have a very straight, clean green boundary. So even though you ramp up those strap pattern ramp up with the rectangular pattern, you're going to have very distinguished lattice orientation within those black area and blue area. Even though you can make the pattern area instead of just a straight line, you're going to have more curved pattern with all those small features. We found that the crystal falling on the system, they can closely following all the curvature forming on the pattern to replicate the geometry of the pattern you print over there and forming the single crystal on wherever you have the pattern to control it. Such kind of pattern also can be controlled by the electric field to switch between two different phases. Here showing you that by apply small amount of electric field, 3.5 volts, that you're gonna trigger the transition from the blue phase 1 to blue phase 2. And during the transition and in each of the phase regime, you can see that as long as you have the pattern area clearly performed, it will following the formed crystal will following exactly the boundary that you draw on the pattern area. Even though it has different curvature over here, but it can can follow the pattern quite well. So based on those information, we start to design this crystal green boundary shape that we have the patterned two different orientation area, and which we found that it provides a very good binary pattern array as a stimuli response optical platform, which can indicate the refraction of the incident laser compared to the boundary that pretty well maintained compared to the without any good controllable boundary here. So those systems, and I'm gonna go quickly, I have a few more slides. The big single crystal system here also provide us ability to study the more fundamental question about how this material gonna be nucleate and nucleate and growth on the pattern area. So we also use the resonant soft X-ray scattering to review the phase transition during the blue phase 1 to blue phase 2. Actually, it following the similar mechanism which we call the martensitic transformation that is observed in the metal material or alloy material. So in order to better use this kind of blue phase, as I mentioned, so far all the study I have introduced to you, that is still based on the material is a liquid state. So if in the future that you want to use for more different application, you definitely want it to be more solid, that you can carry on, you can place on different surfaces. So here that refers how you can polymerize or freeze the structure forming in such kind of liquid phase into a solid phase. here introduce a few work that is do the polymerization of the system to make the material from the liquid phase to a solid membrane material, polymeric membrane material. So here we show that again it can be used as a humidity sensor that be based on the humidity change, the color will be changed. Also can be used since the organic solvent evaporate. And also here shows you that when you add the pressure on the surface, you can like sense the pressure change on the surface. So based on all of that is the material is no longer liquid and they already been polymerized into a polymer material. So in our group that we more care about what is the mechanism behind that when you add the monomer into the system to trigger the polymerization, how the added monomer can distribute it or interact with the blue phase material. So previous work have been done that to show the monomer basically aggregated along the disclination line, but our recent work showing that the adding of the monomer into the system actually participated the self-assembly of the blue phase material to forming the double twist cylinder. Once you have the monomer added into the system, even though you keep the same lattice orientation, however, the monomer add or the synergistic self-assembly together with the monomer and the liquid crystal will change the unit size. Once the unit size change, you will observe the quite obvious color change from blue to green or green to red. So, okay, I think I will finish here. So I hope by today's talk, you're gonna gain just a little bit sense of flavor of what is the liquid crystal and what is blue phase liquid crystal and how the blue phase liquid crystal can work to generate or to be used as a photonic crystal or a sensor based on the vivid color change. So this is my group, and I will stop here, and I'm happy to take any question if you have. Yes?
What is the polymer brush for the liquid crystal again?
Oh, that is the main chain is the polymerisacrylate, and the section we grow or link as the liquid crystal messaging. So if you want to see the
That was the last slide.
last slide,
Yeah.
this.
I was kind of wondering what this. No. Bit further. It was like the second to last slide. That one right there. So I was kind of wondering. A brush for like something, maybe.
Yeah, here like showing you like this is the artwork for a cover image. It's kind of like you have the substrate grafted those brushes, and the section of the brush can be tuned either perpendicular or parallel. And further, if you have small molecular based on the section, it can be oriented this way or this way. Yeah.
Do you see any larger industry applications of this in the next 10-ish years?
So for the, you mean next 10 years?
10 years, 20 years? And
Yeah.
do you see an industry application of this on a large
So,
scale?
yeah, I mean like this thing, from my perspective, that is also the current research conducted in my lab is how we can fabricate the material. For example, use the 3D printing to fabricate the material into like a large area. Meanwhile, with this a large area material that has the stretchability and the flexibility can be used as a wearable device. Meanwhile, because of this specific or very unique structure forming in nanometer scale, can we use the printing to control each pixel? Not by that time it's not pixel, it's voxel, three-dimensional unit orientation. So which means that you have each volume element be well controlled to have like certain wavelengths reflected. So you can imagine that if you have that as a wearable device attached on your skin, it can ramp on your skin, and whenever there will be a signal, you will have the located area like indicate, okay, red color, that is something happened, or green color, that is something happened. Yeah.
Any other questions from the audience?
Oh, yes.
Is the liquid crystal is in a liquid form or other form in LCD monitor?
So in the LCD monitor, they are in the, like in between the solid state and the liquid state. So it is not, it has the ability to flow as water, but won't behave as water without any control. So imagine that you have the electric field signal come in, all the molecules being ordered aligned this way to generate one particular color. Then next the signal comes in, they have to force to change or change into another pattern, right? That is not as water, you cannot order in the water molecules or in this way. Meanwhile, the solid material, for example, metal, it won't be able to transform such quickly from one phase to the other. Use just a small amount of signal or energy. So that is the advantages of liquid crystal.
So is there any possible way to leak if the LCD monitor is breaking or cracked?
Yeah, of course. Yeah, it has such problem.
So it's a little dangerous that if our phones or laptops
No,
display
for nowadays that people also looking for a way that, for example, there will be a way that hold the whole material together. So which means, for example, the last slide I showed to add some monomer to partially cross-link them, to make them still hold as a whole piece of material, but meanwhile maintain their flexibility or adapt to the signal change.
If you have more questions, our speaker will be here for a few minutes, and also, we'd be very happy if you join us for lunch in the Joyce Room of the Corner Cafe. Let's thank our speaker for coming.